Hello, everyone. This is Professor Ma, and this is the introduction to the sections on cylindrical and spherical coordinates. The cylindrical coordinates is just the polar coordinates on the xy plane, r theta, and then you attach the z value to see the height or of the value. So here's the pictures. And the conversion rules between this coordinate and x, y, z, the only things we have to convert is x and y. So we have the polar rules, and x is r cosine theta, y is r sine theta, and z, of course, is equal to z. And these are the standard polar coordinate rules on the xy plane. And so here's a pictures of calculations and converting these cylindrical coordinates into XYZ coordinates. So these are the conversions. Okay. And this is converting backward. And here is a XYZ coordinates. And then we put in the cylindrical coordinates. Okay. So I'll let you figure this out. The reason we call this a cylindrical coordinate is because if I look at some constant functions, r is equal to a constant, z then therefore can be anything. If r is 1, that's a circle on xy plane, but the z could be anything, so I can elevate the entire circle up and down. And so r is equal to 2, then I will get the cylinder of radius 2. That's why it's cylindrical coordinates. If I want to keep track of things on a cylinders, okay, think of one that's in the centers, in the origins, and I'm interested in the coordinates of of a circle around me, but also the height in the cylinders that's created by the circle. If I want to track those locations on these cylinders, then obviously I use cylindrical coordinates. And the constant function theta equal to k, and that of course is at the points in the directions of theta. So I get the plane, this, if you like, a screen, the screen in the direction of 3/4 pi. So this is for r bigger than 0. If r is allowed to be less than 0, I get the entire planes that extend to the other side. Okay. So spherical coordinate. Well, the spherical coordinate, we try to track points on a sphere that's around us. So think of one, it's, think of we are in the middle, in the origins of XYZ coordinate, but we are interested in tracking the points on a sphere. Okay. And let's say the radius of the sphere is rho. Okay. So how can I, keep track of the points on the sphere? Well, to locate the points on the sphere, so what I can do is I can tell you how much you have to rotate. That's the theta, okay, and that how much you have to tilt down in that directions on these, and then that's the point in go the distance rho out toward that directions. Okay, again, you rotate and through the points. So you're inside the sphere and there's a point up there, and you want to locate it, so you rotate. Then you say how much you have to tilt to look at that point, and how much you have to go out to actually get to that point. That's the rho. The rho is the radius of the sphere. And conversion rules. The most important conversion rule is we actually convert use the three numbers, rho, theta, phi, and we convert it first into the for x and y. We'll convert it into the r first. So from this you can see the R is the same as this number over here, so therefore R is rho sine theta. Okay, and then therefore X is equal to R cosine theta. Replace the R part by rho sine theta, and I get these equations for converting to XY coordinates. And now, of course, on the Z level, this is the same as this triangle over here, the height. So therefore, that's a cosine of the Z. So get this conversion. And here I'm just going to scroll through. You can do the calculations, and so this is conversions. Okay. And the reason we call these the spherical coordinates because we are use these to locate points on the spheres. If I'm interested in the location of a big sphere around me with a fixed distance sphere, how do you locate it? I mean, how do you tell the direction? How do you tell the next person, say, to keep track of that point, that star over there? And we set a standard in the coordinate system, and I tell you how much rotating, etc. And this is the spherical coordinates. And then the spherical coordinates is easy to track the cone. If I set phi, that is the angle of tilt, which we call a pitch angle, this angle, again, phi gives you this angle. It's pi over 3. Then all the points on the cone, basically, the pitch angle is pi over 3. So it generates a cone. Here we want to convert equations, so let's do some conversion in algebra. And algebra basically converting to cylindrical coordinate equations. If I'm doing cylindrical, basically I'm looking for x squared plus y squared. Okay, that's r squared. That's the pattern I'm looking for. It has minus r squared. So plug it in. So voila, that's the cylindrical coordinates. Okay. How about spherical coordinates? Well, we can do the same trick. Okay, for the spherical coordinates, I can remember what r squared was. R was rho sine phi. Okay, and z was rho cosine phi. Yeah, I got k squared minus square root equal to that. And this, of course, is squared. R squared. I square both sides. Basically, I wind up clean up. I get the equation rho squared equal to k squared, and rho is equal to k. So after we thought about it for a while, so of course, rho is equal to k because this is the semisphere. Okay, so the distance to the semisphere is rho, the radius. And here is another conversions. X squared plus y squared is r squared, so z equal to r squared is the cylindrical or the polar equation, if you like. And if you want to put into spherical coordinates, z is rho cosine phi and r rho sine phi. Plug them in, then you extract the equation for rho. Usually we write the cylindrical equations in terms of rho equal to something something, because rho in here is the only distance measurements and not angle measurement. If we're going to extract angle measurement, we'll have to involve tangent inverse, involve inverse trig function, which gets a little messier to handle. So, but usually, therefore, it's rho is equal to something in the function form. Okay, and that's it. That's the cylindrical and the coordinates and the spherical coordinates. Okay, bye-bye.